Okay, we're continuing with Chapter 2 in the geometry textbook. In this video, we're going to go through the third section, which is on proving lines parallel. How can we prove that lines are parallel? Okay, for this section, here is a quick review of the relevant postulate and theorems from the section 2.1. Each theorem has the hypothesis if two parallel lines are cut by a transversal. Each theorem has a conclusion involving an angle relationship. All right. If two parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent. That was a postulate, right? The idea is like you draw two lines that are as close to parallel as you could possibly make it, cut them by a transversal, and then use a protractor to measure corresponding angles, and then you see that the corresponding angles are congruent. And you could kind of generalize this. You could draw parallel lines in any orientation, and it seems in general the case is that the corresponding angles are congruent. So that's not an official proof, but it's a postulate. The corresponding angles being congruent was a postulate. All right. Now, if two parallel lines are cut by a transversal, then the pairs of alternate interior angles are congruent. That was a theorem that was built off of this postulate, but we proved this. Okay, then there was the alternate exterior angles are congruent. Okay, now if two parallel lines are cut by a transversal, then the pairs of interior angles on the same side of the transversal are supplementary, and the same idea with the pairs of exterior angles on the same side of the transversal. All right, suppose that we wish to prove that two lines are parallel rather than to establish an angle relationship. Such a theorem would take the form, if something, then these lines are parallel. So if we think about this, the idea is you can think about what is the minimum amount of information that we need to. So if we're going to have, obviously we're going to have some sort of, like, okay, well, we can start with two lines that look parallel in any orientation. They might be parallel, they might not. Well, to prove that whether or not they're parallel, you could cut them by a transversal. Okay, and in that case, you're going to create these angles here, these 8 angles. All right, well, what's the minimum amount of information we need to show about these angles to state that the two lines are officially parallel or not parallel? Let's say lines L and M. So, like, for example, what if we said, well, okay, angles 1 and 4 are congruent because they're vertical angles, so are angles 2 and 3, so are angles 5 and 8, and so are angles 6 and 7. So that proves that lines L and M are parallel. Well, then you would say to that, well, no, because obviously if, let's say we drew these lines L and M and to where they clearly were not parallel, well, that equality, that congruence would still hold between the vertical angles, between angles 2 and 3, 1 and 4, 5 and 8, and 6 and 7. So that doesn't prove anything about whether or not the lines are parallel. Okay, well, if we show that one of the angles 1 and 5 are congruent, is that enough? Or do we need to go further than that? You see, if we showed that these two angles 3 and 6 were congruent, is that enough to say officially, okay, well, the lines L and M are parallel? And once you say that they're parallel, then all of these theorems automatically apply. So that's the way you can think about how we're looking at this. At present, the only method we have of proving lines parallel is based on the definition of parallel lines. Establishing the condition of the definition that coplanar lines do not intersect is virtually impossible. Right, so yeah, you see what they're saying here. If we wanted to, from scratch, think about the idea of how can we prove that two lines are parallel, then we could start with the definition of what parallel is, that you have two lines, they're contained in a unique plane and they don't intersect. Okay, but establishing the conditions of that definition, that you have coplanar lines that don't intersect, that's like, how could you prove that? Just as it's stated. So they're kind of suggesting that we're not even going to think about these angles here or by cutting the lines by a transversal. Let's just think about that the lines are You have these two lines. Let's prove that they're contained in a plane, and now let's prove that they don't intersect. Well, how are we going to do that? That's what they're saying by virtually impossible. How could we possibly prove that? You could think about, like, they need to not intersect over the entire infinite length of the lines. Well, how can you prove for infinity that the lines don't intersect? You could follow this line for 50 miles in one direction and this line for 50 miles in the same direction, and they don't intersect. Well, you got to go another million miles, another trillion miles, light years. And it's still not, and it shows that they don't intersect, and that's still not enough. Thus, we begin to develop methods for proving that lines in a plane are parallel by proving theorem 2.3.1 by the indirect method. Counterparts of theorems 2.12 to 2.15, namely. That's these up here. Theorems 2.32 to 2.35 are proved directly, but depend on theorem 2.31, except for theorem 2.36. The theorems of this section require coplanar lines. Okay, so we're going to begin by, to prove that lines in a plane are parallel, we're going to start by proving this theorem here. If two lines are cut by a transversal so that two corresponding angles are congruent, then these lines are parallel. So here they're saying that all we have to do is, if we have two lines and we want to see if they're parallel, cut them by a transversal and show that just two of the corresponding angles are congruent. Not all of the corresponding angles, just one pair congruent, then the lines are parallel. Then you've proven that the lines are parallel. So we're going to start by proving that using the indirect method. Then counterparts of these theorems, but in terms of proving that, using these counterparts of these theorems that prove that lines are parallel, we'll look at theorems like that and prove those directly, but they're going to depend on this. Okay, now, except for theorem 2.3.6, the theorems of this section require coplanar lines. Okay, so let's keep that in mind. But when they say that all the theorems we're going to prove depend on this, you can think about that in the sense of, like, the corresponding angles postulate is stated first, and then the other parallel line angle relationship theorems depend on that postulate, right? And so you can think about it that way, that here's the kind of starting for proving that whether or not lines are parallel. We start with this theorem, the corresponding angle congruence proving parallel theorem, and then we're going to build the counterpart theorems to these based on this, using this as like the reference. So, okay. So let's prove the theorem that if you can just show that if you can take these two lines that you think might be parallel, or maybe you think they're not parallel, you want to prove that they're not parallel. But actually, let's not think about that at the moment, the reverse of that. What you need to show that, well, we can actually think about that at the moment. So what about the idea that if you can take two lines and you cut them by a transversal, and then you show that a pair of corresponding angles aren't congruent? What does that mean? Well, remember in the previous section, we used the indirect method to prove that theorem was true. That if you can actually find that, again, you find that corresponding angles are, one pair of corresponding angles aren't congruent, then you say you're saying the lines aren't parallel. So yeah, I just want to note that, like, remember these theorems, when you think about the converse of these theorems, those are all kind of their own independent theorems. But what we're proving here, that if you can show that just two corresponding angles are congruent, means that the lines are parallel. We actually already proved the converse of that in the previous section. So, okay, given that lines L and M are cut by this transversal here, we want to, and that angle 1 is congruent to angle 2. That's what we're given. We want to prove that L is parallel to M using the indirect method. So, okay, with the indirect method, and here's an example of, we don't have like a negation type language in the given and the proof, but we can still use an indirect proof. So, okay, we're going to start by supposing that L is not parallel to M. Okay, so suppose that L is not parallel to M. Now let's build some factual statements, use some factual statements and reasons to make a statement about what the given says. If L is not parallel to M, then what does that state about angles 1 and angles 2, about a relationship between angles 1 and angles 2? So, okay, let's see. Suppose L is not parallel to M, then a line R can be drawn through point P that is parallel to M. Oh, yes, okay, and that follows from the parallel postulate because there's only one unique line that goes through a point. If you have a line and a point off that line, there's one unique line that goes through that point that's parallel to the line. So what they're saying is that, so if L is not parallel to M, then we can draw a line R that is 100% parallel to M. That's the unique line, okay? If R is parallel to M, then angle 3 is congruent to angle 2, corresponding angles, right? But angle 1 is congruent to angle 2, according to this. And those are 100% not the same angle. So there's the contradiction. Okay, so there you go. There's the proof. Now, each claim in theorems 2.3.2 to 2.3.5 is the converse of its counterpart in section 2.1, and each claim provides a method for proving that lines are parallel. So, yeah, we're going to now prove the converse of each of these theorems. So, like, if two parallel lines are cut by a transversal, then the pairs of alternate interior angles are congruent. We want to prove that if you can show that a pair of alternate interior angles are congruent, then the two lines are parallel. So if two lines are cut by a transversal so that two alternate interior angles are congruent, then these lines are parallel. Now, it does make you kind of wonder that, well, why don't we need to show that, how come we only need to show, like here, how come we only needed to show that if we show that one pair of corresponding angles are congruent, then that proves everything. Like, why don't we need to show multiple pairs of corresponding angles are congruent? Well, okay, you can think about, well, first of all, the indirect proof was sufficient here. We accomplished everything we need to accomplish to prove that theorem. We proved this theorem here. We proved that if two lines are cut by a transversal so that we just find that two corresponding angles are congruent, then these lines must be parallel. Just one pair of corresponding angles proves that the lines are parallel. That's all you need, just one pair to prove one pair are congruent. So why didn't we need to show that multiple pairs were congruent? Well, again, first of all, the fact that we were able to successfully complete the indirect proof is evidence that you only needed to show that one pair were congruent. And so how can we reason of why this is the case? You know, because it could have been the case that we went through this indirect proof and we got close to doing the proof, but we realized that it wasn't enough just to show that one pair were congruent. We had to go another step. Well, the reason we had to keep going to further steps, it must be the case that you can think about it like, so if we show two corresponding angles are congruent, all right, well, automatically based on the vertical angles, that's going to be congruence there, right? Automatically. So we don't need to prove that if we show these two are congruent, well, we don't need to prove that these two are congruent, right? Well, then if these two are congruent, well, 100% these two are supplementary no matter what. So that fixes that if these two are congruent, then these two must be congruent because they're supplementary. But then you have more vertical angles, you see? And so that you can see why it turned out to be the case that we were able to successfully complete this proof with just focusing on one pair of corresponding angles. If that wasn't the case, if we had to use more than just one pair, it would have become evident in the proof. But the proof clearly showed that, no, that was enough. Once you show that one pair of corresponding angles are congruent, then the lines are parallel, and we just reason through why that ends up being the case, why that's a natural result. Okay. So now, if two lines are cut by a transversal so that two alternate interior angles are congruent, then these lines are parallel. Same idea. We just need to show that if just one pair of alternate interior angles are congruent, then that's going to prove the lines are parallel. So, okay, we're going to do a direct proof here. So given lines L and M are cut by transversal T, but we don't know if they're parallel or not, prove that L is parallel to M. Okay, so the plan is to show that angle 1 is congruent to angle 2 because they're corresponding angles. Then apply theorem 2.3.1, in which congruent corresponding angles imply parallel lines. So, okay, let's see. Angle 1 is congruent to angle 3 because they're vertical angles. Okay, but we're given that angle 3 is congruent to angle 2. We don't know if the lines are parallel. We just know that angle 3 is congruent to angle 2. So that means angle 1 is congruent to angle 2. And then since those are corresponding angles, based on theorem, the first theorem we started with corresponding angles, the lines are parallel. That's simple. Okay, the following theorem is proved in a manner much like the proof of theorem, the one we just did. The proof is left as an exercise. So, okay, if two lines are cut by a transversal so that two alternate exterior angles are congruent, then the lines are parallel. Yeah, you can imagine it's very similar to what we just did. In a more complex drawing, it may be difficult to decide which lines are parallel because of congruent angles. Consider figure 2.18 on the next page. Let me bring this figure down. Okay, so yeah, they're saying it can be difficult to decide which lines are parallel because of similar angles here. Suppose that angle 1 is congruent to angle 3. Which lines must be parallel in that case? Yeah, it's kind of confusing, right? What's the transversals here? What's the lines in question? The parallel lines in question, or potentially parallel lines in question? The resultant confusion, it appears that A may be parallel to B and C may be parallel to D. Yeah. Can be overcome by asking which lines help form angle 1 and angle 3. Line C and line A, and then line C and line B. Yeah, so I think what they're going for here is that if you say which lines help form angles 1 and angles 3. So I just said again, I said line C, line A, line C, line B. Well, then obviously in that case, C, but with these two angles, C is the transversal. And so once you identify what the transversal is, then you know the other two lines are like what lines are in question for being parallel. So, and so in that case, if angle 1 is congruent to angle 3, and we see that C is the transversal, then if we kind of tilt our heads to the left, then upper left or upper right is angle 1, upper right is angle 3. Angle 1 and angle 3 are corresponding, so A and B are parallel. Okay, now here's that same figure. In that figure, which lines must be parallel if angle 3 is congruent to angle 8? So, okay, what they're saying to do is you have angle 3 and angle 8. Which lines are helpful, or which lines form angles 3 and angles 8? So, line C and line B form angle 3, and line 8 is line D and line B. So what's the common line in those two statements? Line B was common to both. So line B is the transversal. And line C and D are being cut by the transversal. So, okay, let's see. So again, angle 3 and angle 8. So upper left, bottom right, so that they're not corresponding. Okay, we can see angles 3, 4, 7, and 8 are exterior. All right. And then they're on the different vertices and opposite sides of the transversal, so they're opposite exterior angles. Well, we just saw with the last theorem that if you find that one pair of opposite exterior angles or alternate exterior angles are congruent, then the lines are parallel. So there you go. C is parallel to D. Those are the B was the transversal. Okay. Now in that same figure, if the measure of angle 3 is 94 degrees, find the measure of angle 5 so that C is parallel to D. Okay. So measure of angle 3 is 94 degrees. They're not telling us that C is parallel to D. They're saying that what must the measure of angle 5 be so that C is parallel to D? Okay, well, we saw that B was the transversal in this case. Top left, those are corresponding, so they must be congruent. The angle 3 must be congruent to angle 5. So also 94 degrees. then they'd be parallel. Okay. Theorems 2.3.4 and 2.3.5, which we're coming up next, enable us to prove that lines are parallel when contain pairs of angles that are supplementary. Okay, because that was another, when it came to angles created by, transversal cutting across two lines, that was another consequence that you had. What was it? It was the pair of interior angles on the same side of the transversal were supplementary, and the pairs of exterior angles on the same side of the transversal are supplementary. So I'm assuming what these theorems are going to say is that if you can show that one pair of interior angles on the same side of the transversal are supplementary, or the same thing with the corresponding pair in the exterior, not corresponding, but the pair of exterior angles on the same side of the transversal, one pair are supplementary, then the lines are parallel. So let's see. If two lines are cut by a transversal so that two interior angles on the same side of the transversal are supplementary, then the lines are parallel. Yeah. And it's going to be a similar type of logic here. Let's see what they do here. So, all right, we're going to do a direct proof. You have lines L and M cut by the transversal, but we don't know if they're parallel, but we know that angles 1 and angles 2 are supplementary. Okay? So, let's see. If angle 1 is supplementary to angles 1 and angles 3 are supplementary for sure because of the straight line here. Okay? Well, and then if angle 1 is supplementary to angle 3 and angle 1 is supplementary to angle 2, then angles 3 and angles 2 are congruent. But angles 3 and angles 2 are corresponding angles. So since those are congruent, the lines are parallel. And then it's going to be very similar to prove that if two lines are cut by a transversal so that two exterior angles on the same side of the transversal are supplementary, then the lines are parallel. Very similar type of proof. Okay. In figure 2.20, which line segments must be parallel if angle B and angle C are supplementary? So if angle B and angle C are supplementary, then which of these line segments must be parallel? Okay, so it'll be easier to think about this if let's extend this. Okay, and then, okay, so if angle B and angle C are supplementary, then we can see those are interior angles on the same side of this being a transversal BC. So lines AB and DC must be parallel. And now we can get rid of those lines and just use those as an aid. So AB and DC must be parallel. Okay, now we include two final theorems that provide additional means of proving that lines are parallel. The proof of theorem 2.3.6 requires an auxiliary line, a transversal. So yeah, if we come back to the beginning of this section, this is when they were mentioning, let's keep this in mind here. They said, except for theorem 2.3.6, which we're about to look at, the theorems of this section require coplanar lines. Okay. So this theorem 2.3.6 isn't going to require coplanar lines. It's going to require an auxiliary line. All right. If two lines are each parallel to a third line, then these lines are parallel to each other. Okay. So theorem 2.3.6 is true even if the three lines described are not coplanar. Yeah. So we talked about this. I'm not sure what video before this we talked about this, but yeah, this is, so, okay. We can reason through this without going through an official proof, but we'll still look at the proof. So, okay, if you've got this line here and this line here, and they're parallel, okay? Line L and line M. So since they're parallel, they're not skewed. There's a unique plane that contains the lines, right? So let's think about the case where out of this plane, there's another line over here, let's say back behind this plane, but it's parallel to one of these lines. Let's say line L, okay? So it's not, it's definitely parallel to one of these lines. Let's say I'm going to choose line L, okay? So I can only really draw it this way. I can't draw it. I can't like draw it like this. That would be, it would be skewed to line L, right? I have to draw it a certain way. It doesn't have to be, let's say this is plane P. It doesn't have to be in plane P, could be, but it has to be in a certain orientation or else it's going to be skewed from line L. So I have to draw it in a certain way. So let's say this is line N. Okay, so line L is parallel to line N, so that means those two lines are contained in their own unique plane. Kind of looks like line N is above plane P, which is, that's fine. So this is plane Q. Okay, so we've got line L is parallel to line M, and line L is parallel to line Q. What they're saying is that, well, actually, this is not quite what they're saying. They said if you had two lines that are each parallel to a third line, so they didn't say that. We didn't have to start by saying lines L and M are parallel. But let's keep going here because we can still see the same idea. So, okay, let's say lines L and M are parallel, and then lines, or no, this would be line N, and then lines L and N are parallel. Well, then line M and N are going to have to be parallel as well. You see? Now, that's not exactly what the theorem was saying. What the theorem was saying was that you actually started off with line L is parallel to line N, and line M is parallel to line N. Therefore, line L must be parallel to line M. That's what the theorem was saying, but either way you look at it, it's all the same idea. So like this is going to be in its own plane, line L or line M and N. And the reason is because since L is parallel to N and M is parallel to N, it's like you couldn't draw any of those in a skew orientation for them to be parallel. So that means that L is not going to be skewed from M. And so that means they're going to be parallel. That's not an official proof. We'll look at the official proof, but I think this should give you some intuition for this. Now, just note, though, that we're not saying that they're all kind of parallel at the same time in the way that if you drew line in plane P, then it's kind of like they're all parallel as a unit, which we haven't really talked about that as an official idea yet, but like you couldn't say that like as a group, L, M, and N are parallel as like one group because it's not one unique plane. But if you drew line in plane P, then you could kind of say that, but we haven't really officially talked about anything like that yet. Okay, now, theorem 2.3.7, if two coplanar lines are each perpendicular to a third line, then these lines are parallel to each other. Okay, so if you've got two coplanar lines, but they're not the same line, and both of those are perpendicular to a third line, they're perpendicular to the same line, then the two original lines must be parallel. That's interesting. I mean, intuitively, it makes sense. If you've got two lines that aren't the same line, and you can find one other line that's perpendicular to both of those lines, so let's say this line's perpendicular to this line, but you can't make it perpendicular to the other line, right? The only way you could make it this perpendicular to both lines would be like these two lines here need to be parallel. Interesting. Okay. All right, so the proof of this theorem we just talked about depends upon establishing the condition found in one of the theorems, that the previous theorems that we learned in this section. Okay, in example 5, we established congruent corresponding angles in statement 3 so that lines are parallel by theorem 2.3.1. So, all right, let's take a look at this. Given AC is perpendicular to BE and DF is perpendicular to BE, then AC and DF must be parallel. So, okay, you've got those two lines are perpendicular, then that means that angles 1 and 2 are right angles, yeah. That's what perpendicular is, that's a result of being perpendicular. So angles 1 and 2 are congruent. And since those are corresponding angles, the two AC and DF must be parallel. There you go. All right, given that the measure of angle 1 is 7x and the measure of angle 2 is 5x, Find x so that L will be parallel to M. Well, you need, for those to be parallel, you need angle 3 to be congruent to angle 2 as corresponding angles. So angle 3 is going to be 180 minus angle 1. So you need 180 minus the measure of angle 1, which is 7x, to be equal to the measure of angle 2, which is 5. They give us as 5x. So 7 plus 5 is 12. And then 180 divided by 12 is 15. Okay. Now they do a construction, which depends on theorem 2.3.1, which they restate that way we learned this earlier, that if two lines are cut by transversal so that two corresponding angles are congruent, then those two lines are parallel. So the construction that they do is that they want to construct the line parallel to a given line from a point not on that line. Right? So there's going to be one unique line that goes through this point P that's parallel to this line. That's the parallel postulate. Okay, how can we use a compass to construct that line in a straight edge? Compass and a straight edge, potentially a straight edge as well. So, okay, let's see. Okay, first, draw a line to become a transversal through point P and some point on line AB. So, okay. They draw this line that goes through point P and then through some point on line AB. Okay, now using P as the vertex, construct the angle that corresponds to angle PAB so that this angle is congruent to angle PAB. It may be necessary to extend line AP upward to accomplish this. Okay, so how can you construct an angle so that you want to construct like you want this angle to be congruent to this angle. You haven't drawn line PX yet. So how can you do this? Well, in chapter 1, we learned how to construct angles that are congruent to other angles. Okay, if we come back to chapter 1, this construction 3 here. So construct an angle congruent to a given angle, congruent to RST. Okay, we're going to start with this ray PQ here. It's going to be one side of the angle. That's going to be congruent to RST. So now, with a compass, come to this angle and mark an arc to intersect both sides of RST at points G and H. So you put the center at S and you mark an arc to intersect both sides here. Okay, now without changing the radius, mark an arc to intersect PQ at K in the would-be second side of NPQ. So without changing the radius, you put the center of the compass here. It intersects at K, and you just make sure it goes plenty long enough to where the would-be side is going to, what you would expect for the congruence. Okay, now mark an arc to measure the distance from G to H. So, okay, you put the center of the compass here and the pencil out here, and you mark this arc. Then you come here and you do the same thing. You mark off that arc, and then you draw the line through the intersection. Now you have a congruent angle. So, okay, using that same idea here, we put the center of the compass at A, and then we would draw an arc that goes through both of these lines. But they do it to where they draw the arc to where it goes through point P, but you don't have to. Then, without changing the radius, you put the center at point P and draw that same arc. And then make sure it extends past the horizontal. Okay, then you put the center at point P and you put the radius here. And then you draw this arc. Then you come to this intersection point. You probably have to extend this line up. And you draw that same radius. And where it intersects here, you make line P through that intersection point. And now you know that this angle is congruent to this angle, which means that you've drawn two parallel lines with one of the lines going through point P.